let's jump into our currently empty position control file. I'll start by just defining this header guard so that we can only include this function once and we don't run into certain compiler errors. And then I'll define our class. Our class will have some private member variables, but it should also have a public constructor. It'll also have a setup method, and it should also have a loop step method. So that's the basic setup of our position control, or really any header that we create for this class. Jumping over to our INO file, we can start filling in the blanks here too. We'll have our position control object, and we need to tell the IDE where it can find that file, and the compiler when the time comes. Since this is a file specific to this exercise and not code that I'm giving you, since it's code I want you to write, it won't be inside one of these include directories. It'll just be existing alongside the INO file itself. Alright, so we have our position control object. We'll call setup. And of course we'll call its loop step. Alright, we have the basic setup here. Now we can dive into our actual implementation. So what does position control need? Well, it needs a goal position. And since this is position and not pose control, we don't really care about the final orientation. We just care about the final XY coordinates. We also care how close you get to those XY coordinates. So I'll also introduce a threshold. So we don't have to be exactly on top of this X and Y position, but as long as we're close enough, we'll say that we're at that position. This is a proportional control class, much like our motors themselves are proportionally controlled. So we'll have a proportionality constant for the position, and one for the orientation. We also want to put limits on how fast we're allowed to change the angular or linear velocities. So a user needs to specify a max linear and a max angular velocity. So starting with those, we have to decide whether it makes sense to put those in as the constructor or the setup method. And since these is all plain data, it doesn't matter if we initialize all these variables before the Arduino setup. So we can just initialize those as part of the constructor. So I will put them all here. Sorry for all my misclicks. Now we need values to actually populate each of those. And they need to be separated by commas. Including this one. Oh, that one looks like it might just be a typo that happened somehow. These are all values that I'm going to expect a user to pipe in. So I'll add them here as arguments to this, and then just change all these semicolons into commas. And remove the trailing comma. Alright, so now a user, when they specify that they want to do position control, will have to pass in all those values. And then we initialize with the values that are passed in here. So the member variable goal x will be initialized with the parameter goal x, and so on for the rest of them. So now if I go back to our main sketch file here, we'll need to specify those. So a goal x, and we'll say that that's a constant. Same with the goal y. And the goal threshold, we've already specified a max linear velocity, but now we also need a max angular velocity. We need our gains for position and orientation. And that's all of our arguments for our position control. Arguably, this value for max linear velocity does not have to be the same that we use for the motor control itself, but I don't have a good reason to specify something different, so I'll leave it as the same value. Let's specify our first goal just to test things out at 1, 1. And let's say if you get within 10 centimeters, that's close enough. I'll leave the max angular velocity separate from max linear velocity and just specify it here. This has some physical meaning. It's how many radians per second are you going to allow your robot to rotate. This is a value you should use your simulation from the Tuesday part of the exercise to find a good value for the max angular velocity. Next, we need the control gains. And the exact values for those, again, are things that you should play around with in simulation. I'll initialize the values that I found worked well for my particular setup. And now we've specified all of the obvious values for positional control, and we'll want to now implement both the setup and loop step functions. In this case, much like some of our other headers, we don't actually need to do anything in setup. There's no additional functionality, no pins that need to be accessed, no microcontroller initialization that needs to be done. So I'll jump down to the loop step method. And much like it was on the pseudocode for the Tuesday lecture, for this we're going to need to pass in a pose, and that's the current pose. And we'll also need to pass in a left velocity and a right velocity. This header file doesn't know what we mean by pose. That's defined in the forward kinematics header. Similar to our kinematics, we don't necessarily want to change or update position control as fast as possible. Instead, what we'll want to do is we'll only want to do something if an update timer has triggered. And so this is code from my example, and it won't make a ton of sense here, so let me fill in some of the blanks that are in position control. But first, let me initialize an update timer. Which means we need an interval. And we need to update or construct our update timer object. Okay, the compiler error is indicating that I have void here, but I have a boolean here. So what's going on? Well, what I found when I was implementing this for the first time was that for position control, every time I call loop step, I don't necessarily produce an output. So by that I mean sometimes the timer hasn't triggered and I don't want to actually update the motor velocities. So that is what loop step will return, a boolean to indicate whether or not we should actually update the motor velocities. Speaking of which, now that position control is going to set the velocities, I should get rid of their initialization inside the setup method, or setup function as it is. For loop step, I need to pass in a pose, a left velocity, and a right velocity. It's the same pose that I'm getting from forward kinematics. So I'll just rearrange that code a little bit to put the pose there. Now it might seem odd that I'm passing in a position velocity into position control. And that's because the goal is for position control to return the left and right velocities. So it'll return false if I haven't updated them, and true if I have updated them. The C++ language doesn't have real strong support for what are called optional values, which is what I would normally use if I were writing in something like TypeScript or Rust, or OCaml or Haskell, or you pick your functional programming language. So instead, the way you do this in a language like C++ or C, you can actually mimic that type of functionality, but a more common pattern to see is to indicate a bool as the optional part, and pass to pass in variables, parameters, as references. So pass them in by reference. And so what I'll do in this function is I'll set left velocity and right velocity. And since these are passed in by reference, it'll actually mutate the values that I'm passing in here. No need to define new variables, I'll just reuse the variables that are already defined up here. And since they're being passed in by reference, when this position control loop step function ends, those two variables will be changed to whatever the position control needs them to be to drive the robot towards its goal position. So now, I just need to know if I should update the velocities, and if I need to, I'll tell the motor control object to set target velocities for both the left and right motors. So a quick summary here. Position control is in charge of setting left and right velocities, but it doesn't do so every time because it doesn't need to update at the fastest possible rate. Instead, it'll indicate whether or not it has updated the velocities, and if so, we need to set the motor commands to those velocities that were computed by the position controller. So that means we need to interpret VL and VR here a little bit differently. I'm not actually plotting this inside the web interface, but that data is there if we wanted to create a second plot. Instead of these being the current values, the current speeds of the left and right motors, they're the current desired speeds of the left and right motors. So a small change there, because we might not be going exactly the desired speed as set by the position controller. And now there's only one last thing to do, which is to actually implement this inverse kinematic step. So we first need to see how far away from the goal pose are we. Assuming I have no typos here, this should be the Euclidean distance to our target goal position. And if we're less than the threshold away, all we need to do is these two lines of code and return. No need to do more work after that point. If we're not there, we need to compute both v and theta dot. And we'll use those to set the left velocity and the right velocity. To set the left and right velocity, we also need to know the track width. So that's the final parameter for this class. Our linear and angular velocities that we need to get to the goal position, that's our proportional controllers. So we'll have our proportionality constant for both. And those will both be multiplied by the error. So the error in position is given by d, the distance to the target. And the angle error is something we need to do a little bit more to compute. But I also want to take this time to use our max linear and max angular velocities. Because we're not just doing proportional control here, we're also limiting the values that the controller is allowed to use. So we want the minimum between the computed control values and the limits. So V is now done. That's our Alright, so what is our angular error? Our angular error is the difference between the angle to the goal and the current heading of the robot. Which means we need to compute the angle to the goal. And that's from our current position to the goal position. And that's it. That should be the end of our proportional controller. And given the way that I've set it up, that should be the end of our main code here as well. Now we just need to tell the positional controller the track width of our robot. And the update frequency. And let's set that at either half a second or maybe a quarter of a second. That's another value that you can play around with. Alright, just double checking that I have track width defined properly. Alright, the last thing to do is to see if this code compiles and runs. The code compiled and uploaded. Now time to send some heartbeats and see if it runs to its position. Full disclosure, I tested it once before running the video. That's why it thought it was already there. So I'll send the reset again. Stop sending heartbeats, send the reset, clear the plot, start sending heartbeats again. It'll think it's at the initial position, and it should track to position 1-1. The robot is clearly sitting on my desk. It doesn't know that its wheels are up off the ground. So it thinks it's at 1 meter to the X direction and 1 meter in the Y direction away from its original position. If I were to put this down on the ground, due to imperfections in control and slipping of the wheels, maybe my control is too aggressive and it slips really harshly. Maybe the surface of the ground is slippery. Maybe there's some sort of debris in the way that knocks it off course a little bit. It's unlikely to get to exactly that position 1 meter away on the 2 axes, but it's likely to get close enough. And in later chapters, we'll see how to characterize exactly how close it should be to its goal position. The last thing I'll mention is that I added a widget to the chapter for this set of lecture videos, which lets you do things like figure out how your robot's behavior changes if you change the goal positions. So for example, if I put the goal position pretty sharply above, but I don't let its angular velocity be high enough, it'll make it really difficult for it to ever reach that goal position, and it can get stuck sort of spiraling here. There are a lot of different things we can do to sort of torture our robot and not let it meet its goal position. So I'd encourage you to play around with these sliders, and you could use this in addition to your simulation to figure out good values for the gain for position and the gain for orientation, as well as the maximum angular and linear velocities.